Bonjour to everyone. First of all, I would like to thank Dr. Frédéric Barbaresco for giving me the possibility of giving the present talk in front of all this virtual and physical audience. My idea is that although we never met, Barbaresco and I share the same basic idea that the field of machine learning will make significant advances in spite of all the successes that has already been piled up by introducing a larger fraction, a larger component of advanced geometrical mathematics in its real tissue. In particular, I think, and this is my own viewpoint, that the type of mathematics that is needed in this field to make further advances is largely overlapping with the phys math that was developed over the last 50 years in the field of supergravity and superbrains. And that justifies my title, From Supergravity to Machine Learning. And the specific title of today, Souriau Thermodynamics on Kähler symmetric spaces. In the next slide, we can just grasp the spirit of my own talk in a figurative way, and I try to illustrate it because it is a sort of picture-wise summary of what I'm going to talk about. On one side, there are non-compact symmetric spaces, U over H, where U a simple group and H is its compact, its maximally compact subgroup. On the other side, there are solvable Lie groups, where solvable S is necessarily a subgroup of U. It is an heritage, as I will illustrate in a moment, of supergravity, the proof that every non-compact symmetric space is equivalent as a differentiable manifold to a solvable Lie group of the same dimension, the metric equivalence. I will advocate that U over H are the correct model for the layers of friendly neural networks that have covariance. On the other hand, we need also to do thermodynamics. That will be my viewpoint and my next item on such manifolds, because we need also probability viewpoint in machine learning. In order to do thermodynamics on U over H, I will show that it is necessary that U over H be a Kählerian space. That opens the way to do Souriau thermodynamics on such manifolds. So here we have King Arthur in the how to say, in the role of geometric deep learning. On the two sides, two paladins, Cartan, whose lifetime work had one of the main monumental successes in the classification of symmetric spaces, and on the other hand, Hadamard, because one of their common works is particularly relevant in this field, as I will shortly demonstrate. So let's go to the next slide, where I advocate that geometric deep learning has necessarily two main pillars, is founded on two main pillars. On one side, differential geometry, which is the frame in which network layers should be modeled, and on the other side, probability theory, because all algorithms in neural networks are typically ending up in probability theory framework, in the probability theory framework. This been given and accepted as a matter of fact. Pillar one is the first where I have to talk about, because I cannot talk about the second pillar, which is the focus of the seminar, and it is the topic related to the subject. I cannot talk about the second pillar without summarizing the new vision and format that we developed, meaning me and my co-authors and collaborators, the new vision that we developed about the first pillar. So, concerning the first pillar, the point is that we developed a global geometric approach to machine learning from first principles, rather than case by case, rather than working in a case by case approach. Let us begin with the preamble on the global geometrization of machine learning that ended up in the proposal we put forward of so named by us, Cartan Neural Networks. This is a long-term project that started in 2023, and it pays a few moments to describe how the project was born. Stimulated by my friend Sauro Ditati to think about machine learning and phys-math, in the spring of 2023, I tried first to learn what neural networks are, next to think which conceptual contribution I might provide to this field. Unexpectedly, I discovered two things. The standard conception of neural networks, notwithstanding their great successes, is plagued by an original sin, a mathematical discrepancy that is quite serious. Yet, it is essential for the functioning of the algorithms as they are mostly formulated at the present day. The removal of this original sin can be obtained by importing into machine learning a large fraction of the mathematical lore developed in the context of supergravity on the basis of the advanced classical differential geometry. That is the second point. These two discoveries led to the development of a presently ongoing research project, which has already produced 6 ponderous papers, all posted on archive in the just in the past year, 2025. I will quickly go through this without commenting on the content of each papers, just for quick information. The sixth paper marked in black, is the focus of the present-day seminar. So, what is the critique of present-day neural networks that is at the basis of the new development that we have made in this last year? It is the following. The conventional neural networks evolved as multi-layer arrays of perceptrons historically, and inherited both the neurophysiological naming of their components and with them an original scene that we describe below. Yet, mathematically, they are something of completely different nature. They are just a construction of a large number of parameter ansatz for an unknown function that has to be interpolated from examples, the so-called learning. The basic idea how to construct this large parameter ansatz is that of making a succession of maps from an original input data, that is the data, and a final output, by going through intermediate steps that are the hidden layers. X0 is the data, represents the data corresponding to a point, and each intermediate vector, xi, is computed through a function similar in spirit to the perceptron transformation, namely an affine map followed by a nonlinearity. So, schematically, this is how the vector xl is produced starting from the vector xl minus 1. We do an affine transformation. So we have a matrix, typically rectangular, because the dimension of the xl and xl minus 1 vector spaces are different. We make such a affine transformation given by a linear transformation encoded in the rectangular matrix W, that is called the matrix of weights, followed by a translation with the vector BL of the dimension of the target manifold, the target vector space. And that is called B because in the nomenclature of machine learning, this is called the bias. But the next point is the original C. There is the nonlinear map phi of L. That is a nonlinear activation function, namely a one variable nonlinear function, typically mapping the full interval of the real numbers into the interval, the finite interval 0, 1, that is applied to each individual component of the vector obtained through an affine transformation. This is clearly the original C, because such a thing destroys completely the nature of the vector space and destroys the possibility of making changes of basis. So the construction of the ansatz should be mathematically well defined, self-consistent, and the most important thing, interpretable within a geometric and or an algebraic theory. This interpretability of the map is essential to make covariance of the full network and allow to interpret the outputs, the way the outputs are constructed in some mathematical way, so as to be able to understand why a given answer is given, not only what the answer is. Mathematically, the definition of the linear map we have shown is anomalous, independently of the choice of phi, the activation function, since it's not covariant with respect to change of basis in the vector space Vn. Definition of phi makes sense only on a specific basis. Furthermore, the list of activation function phi, commonly used, has no intrinsic characterization of any algebraic, analytic, or functional nature. It is just a collection of ad hoc objects. In the geometric setup of Cartan networks, on the other hand, where the maps from one layer to the next are homomorphisms and isometries, this conceptual problem is overcome from the very start. So, what is the conception of Cartan neural network? This comes from the following short discussion. The vector spaces Vn must be interpreted not as vector spaces, just as coordinate patches for a differentiable manifold Mn. The layers are not vector spaces, but must be Riemannian manifolds, differentiable manifolds. The layers of such must have such a nature. Secondly, the maps from one layer Mn to the next Mn plus 1 must be smooth maps between manifolds. But in some way we should keep the spirit of the neural networks, namely we should obtain maps from a manifold to the next one that are the outcome of a linear map. Otherwise, we lose the idea of the weights, which is the main core of neural networks function. The only general way to obtain a nonlinear smooth map between manifolds from a linear map between vector spaces is when the considered manifolds are Lie groups Gn, and we work out the map from one Lie group to the next one among adjacent Lie groups that is generated by a linear map instead on the corresponding Lie algebras, among the corresponding Lie algebras. In view of the above, the nonlinear map that substitutes the activation function has to be conceptually the conceptually unique exponential map from Lie algebra to Lie group. It can be done in various different ways, but it has to be the conceptually unique exponential map. Now, what makes this argument concrete is what follows. At first sight, it might seem strange that the network layer should be Lie group manifolds. Yet, there are general theorems that come in our aid if we think about what are the basic needs of neural network algorithms. In all neural network algorithms, the view of data is that they are points, sometimes surfaces, in a space, and we analyze their relations on the basis of the relative distances of these points. Points that are near to each other are correlated, while those that are far away from each other have weak correlation. That is the basic qualitative idea behind all the algorithms. But the word distance is the key word. Hence, the manifolds Mn, we arrived at that before, must be Riemannian manifolds, admitting a unique notion of distance between their points. On the other hand, the second point, only relative distances must be relevant. Namely, all points of each manifold Mn, that is the modeling of a neural network layer, should be equivalent. This means in mathematical speech just another word. The manifold Mn should be homogeneous spaces. So let us see what fundamental mathematics tells us about these two requirements. The Cartan neural networks follow from first principles. The issue of thermodynamics on Lie groups, consequently, that is why this discussion is very important before we enter the matter, the topic of Souriau thermodynamics. The issue of thermodynamics on Lie groups is not just an option. It is imposed by what follows from theorems once the two requirements of distance function and homogeneity are accepted. What are the theorems? The theorems are, first of all, that in order to have a square distance function between any 2 points of the Riemann space, it is necessary that the geometry of the latter provides a unique geodesic arc connecting any pair of points. Then the distance will be just the length of such an arc. Now, the only simply connected smooth manifolds with the above property are the Cartan-Hadamard manifolds that are mathematically defined as those non-compact, simply connected Riemannian manifolds whose sectional curve is non-posited at every point. Now, a very significant theorem on Cartan-Hadamard manifolds defined as above is the theorem by Cartan and Hadamard together, namely that every Cartan-Hadamard manifold MD of dimension D is diffeomorphic to the Euclidean space RD. If we need homogeneity as well, then the only generic option is that our Cartan-Hadamard manifold should be Alexeyevsky normal Riemannian spaces. So let us discuss the notion of Alexeyevskian spaces. An Alexeyevskian normal Riemannian manifold is a Cartan-Hadamard manifold that admits a solvable Lie group S of isometries with free transitive action on M. By definition, as a differentiable manifold, an Alexeyevskian space is just the solvable Lie group manifold S. As by definition, an Alexeyevskian manifold is a pair of a Lie group, a solvable Lie group S, and a metric which is derived canonically from a Riemannian metric that is derived canonically from a norm, namely a symmetric quadratic form on the corresponding solvable Lie algebra, and this norm must be non-degenerate and invariant under the Lie algebra, as defined in the next equation. Now, this normed solvable Lie algebras are studied and classified. There is an entire mathematical literature of them, and once we have a scalar product, a non-degenerate scalar product on the solvable Lie algebra, we have automatically a Riemannian space on the corresponding Lie group. Now, what is Sugra heritage? The Sugra heritage is that the metric equivalence on non-compact symmetric spaces, U over H, with a solvable Lie group. In three words, in three lines, every non-compact symmetric manifold, where U is the Lie group corresponding to a Lie algebra that is a non-compact real section of a simple Lie algebra. Every of these manifolds, symmetric space, is equivalent to a suitable solvable group, which is a subgroup of the entire U. And obviously, U is H is the maximally compact subgroup. Now, this means that there is a unique non-degenerate form on the corresponding solvable group that corresponds to the unique Einstein U invariant metric on the symmetric space. The concept of this equivalence was elaborated first by myself and Tujant in the middle 1990s, and then developed by the same authors with Adrianopoli, Dauria, Ferrara, and also some other authors. This yields what we named in the context of supergravity the solvable coordinates on U over H. Solvable coordinates are the Lie group parameters for the solvable group. The solvable coordinates are the explicit realization of the diffeomorphism claimed by Cartan-Hadamard theorem between U over H and Rd, where d is the dimension of U over H. This is a great result. Using only the requirements of homogeneity and existence of the distance function, we have selected those manifolds that are symmetric U over H spaces and are metric equivalent to as many solvable Lie groups. Since they are Cartan-Hadamard manifold, they are diffeomorphic to Rn, and that we have already said. Namely, there exists just one cart, and this is provided by the solvable coordinates, just one chart that covers the entire solvable Lie group. Now we are in a position to make our proposal for the new Cartan neural networks, namely single out what are the hidden maps between the layers. In a very short speech, because my focus is the next pillar of corresponding to probability theory, the structure of the layer to layer maps is described in the following. I do not go into the details, but there is some way of representing with the symmetric matrix a generic point on every of the non-compact symmetric manifold Ui over Hi. And there is a well-defined operation omega var omega I that maps this is the explicit realization of the metric equivalence into an element of the corresponding solvable Lie group. Then, with the map that we call sigma -1, which is essentially the logarithmic map, we step down from the Lie group element to the corresponding Lie algebra element, solvable Lie algebra element. Y are the solvable coordinates. Then we make a homomorphism of the solvable Lie algebra I into solvable Lie algebra I plus 1. Homomorphism because the dimension of the two Lie algebras can be different and typically are different. So it should be respected the structure of the Lie algebra, but there can be a kernel or a co-kernel. So this is the linear map. Then it is obvious what we can do. We can make the exponential map from this Lie algebra element to the corresponding solvable group Lie element, and then the inverse of the map omega I, which gives as image the corresponding point in the next ui plus 1 over hi plus 1 symmetric space. This that is the the overall map associated with W is the generalization of the linear transformation. To this we have to add the generalization of the translation. What is the generalization of the translation? It's very simple. It is the action of the arrival ui plus 1 group on the symmetric space. Namely, any element of G can be let to act on the point represented by a symmetric matrix of the arrival layer. So it is just such a transformation, and that gives the final new point. The parameters of the U transformation are the generalizations of the biases, and this construction here is the generalization of the symmetric transformation. As a consequence of this alternative way of constructing the neural networks, we have covariance, because the map Ki can be transformed in its hidden parameters by a generic transformation on the right with an element of the ui group, on the left with an element of the ui plus 1 group. And the biases and the W map, the W matrix representing the homomorphism will change accordingly. So this means that the learnable parameters have now a clear-cut geometrical meaning, and they can be studied a posteriori after training, and also brought hopefully to some normal forms by utilizing covariance. So finally we arrive at the second pillar. Next we discuss the second pillar. The yields of our previous analysis imply that we need probability distribution on solvable Lie groups, hence Souriau Group Thermodynamics. My discussion will go through 3 steps. In the first step, I will discuss the general setup of geometric thermodynamics defined by a collection of functions xi of q are the parameters on the of a coordinates of a generic point on the manifold of events omega. The manifold of events is modeled as a differentiable manifold. So, given a set of functions xi of q that we are interested in on a manifold of events, we can construct generic thermodynamics. A contact manifold structure emerges in the thermodynamical space that is always odd-dimensional and has a sort of foliation, it's not a real foliation, in Kähler codimension 1 leaves S of dimension 2n, and this I will put into evidence. Now, in the second step, we ask ourselves which are generically the interesting function xi of q to choose in the construction of thermodynamics. The choice is that they should be moment maps of vector fields acting on belonging to the tangent bundle to the manifold of events. Now, in order to have moment maps, that requires that the manifold events should not be a generic manifold, but a symplectic manifold, should be endowed with a maximal rank differential to closed differential to forms. More generally, we will see just mention that it might be relevant to use functions that are not only moment maps of vector fields, but more generally polynomials in such moment maps. In the third steps, we come at a bifurcation. Either the manifold of events is the phase space of a dynamical system and the moment maps are really Hamiltonians, typical in involution, or, and that's the second option, the manifold events is a Kähler manifold with a maximal group of isometries. The relevant moment maps, in that case, are those of Killing vector fields. And that is how Souriau thermodynamics emerges. So let's see geometric thermodynamics in general. There is a general relation between thermodynamics, that is a macroscopic view on reality, and probability densities, that is a microscopic view on reality, and their entropy, according with the brilliant definition of information entropy by Shannon. If we take into account this general relation, thermodynamical equilibrium states are defined once again in a geometrical way as Lagrangian submanifolds in symplectic geometry. And that provides the link of thermodynamics with geometry. And from here we arrive at the generical way of introducing a geometry of thermodynamics, which is what in the machine learning community is named information geometry. Now let's see this general setup. In the general setup we have a probability density on the manifold of events. And the Shannon entropy functional is defined, as most of you are surely aware, know from their youth. Then, in 1957, James retrieved classical statistical mechanics from the principle of extremization of the Shannon entropy at fixed mean values. The mean value of a function that is of interest on the manifold of events is obviously given by this integral. Now, maximizing the extremizing with the variation calculus Shannon entropy at fixed mean values means that we impose by means of Lagrangian multipliers the constraint that the average value of the function x should be a certain given number that we call small x. At this point, the extremization is a classical problem, and it leads, if we take into account also the normalization of the distribution, of the probability distribution to 1, integral should be at the end of the day 1, leads to the extremization of the following functional. Auxiliary functional, the functional Shannon functional, plus introducing this vector of a Lagrange multiplier called lambda, for I don't say how many of these guys are, and just a single lambda 0 for the normalization to 1 of n. The outcome of variation calculus is that the final distribution is what we call a Gibbs distribution, namely the exponential minus lambda fq divided by the partition function, which is what assures the normalization to 1 of r of x. The partition function is just this integral over the manifold of events. Mu is the integration measure. Now, thermodynamics, as we know it from our high school or early university years, is physical thermodynamics is such that it contains two types of thermodynamical variables, the intensive variables and the extensive variables. For instance, in physical thermodynamics, an intense variable is temperature, and other are the chemical potentials. The extensive variables are, for instance, the internal energy and the volume. Now, in this geometric approach, generalized geometric approach to thermodynamics, the intensive variables are the Lagrangian multipliers, where the extensive variables are the values, the mean values of the functions we consider. This general setup leads to contact and symplectic geometry for thermodynamics. So I have to spend a few words on contact geometry. Contact geometry in a nutshell. I cannot speak too much about it because that might be an entire course in a chapter of differential geometry. But in a nutshell, a manifold of odd dimension, necessarily odd dimension, has a contact structure if there is a rank 2n subbundle, where 2n plus 1 is the dimension of the manifold, a rank 2n subbundle of the tangent bundle that can be identified with the hyperplane bundle generated by one form that is called the contact form, and the real definition is, of the contact structure is provided in terms of the properties of the contact form alpha. The contact form alpha should obey the following condition: that alpha exterior product with as many times its own exterior differential as are the dimension n should be different from 0. Namely, alpha should be like that never intersects any of its differential two-form differentials. The contact form is any one form satisfying this constraint is called the contact form, and the contact structure, namely the reduction to a sub-bundle, is given as the kernel of this contact form, namely all those vector fields on m to n plus 1, such that alpha evaluated on them makes 0, are those that span the contact structure. Now, I skip all other details on contact geometry, but I mention a very important theorem, classical theorem of the 19th century, that for every contact manifold, in every open chart, one can find Darboux coordinates, namely coordinates such that alpha is represented in the way displayed here. There is an exceptional x coordinate, x0, and then n pairs of coordinates y and x's, such that the one form, the contact one form, has this structure, the Darboux form. This is what makes the connection with thermodynamics. The whole of general thermodynamics is encoded in stating the expression of the contact one form. The contact one form is alpha, has this structure where d of I is the exceptional part, and I is the Shannon entropy, and the other coordinates are the Lagrangian multiplier and the corresponding mean values, xi. So this is how thermodynamics is linked to geometry, by writing the contact one form. Now let's look at what happens in classical physical thermodynamics. In its simplest form, we can think of a thermodynamical system as being described by 5 variables: the entropy, S in green, the temperature, and the pressure. And by the 2 extensive variables, U and V. Now, actually, we should identify the 2 lambdas in this case, with 1 over t and with p over t. S is the entropy, and U and V are the 2 mean values associated, the first to lambda 1, the internal energy, the second V to lambda 2. Now, if we do that, we arrive at writing the contact one form in this way. The Shannon entropy is always the negative of the physical entropy. And with the previous definition, we write this. Now we see that stating that alpha, the contact form, vanishes is equivalent to the first and second principle of thermodynamics. I do not comment on that too much because I think it is very simple and everyone understands that this is the first principle and this is the second principle, and together putting the 2 together means to make the alpha form being 0. But now comes the real mathematical question. What does it mean that alpha vanishes? Obviously, alpha cannot vanish a priori everywhere because that would destroy the whole interpretation. The fact that it vanishes, it means that it is zero on certain submanifolds of the thermodynamical contact space. These submanifolds are the thermodynamical equilibrium state. So the equilibrium states we are going to claim are Legendrian submanifolds. So first of all, let us say what is an isotropic submanifold of any contact manifold. An isotropic submanifold is a manifold whose tangent bundle is in the kernel of the contact form. Namely, the tangent bundle to a Legendrian submanifold vanishes. The contact form on the tangent bundle of a Legendrian submanifold vanishes. When the isotropic submanifold is of maximal dimension, it is named a Legendrian submanifold. So the full geometrization of thermodynamics that was clearly described by Lichagin and Ropp in some lecture notes, and that is the completion of Jane's work on reinterpreting thermodynamics and statistical mechanics from information theory, a la Shannon, is described by saying that the equilibrium states are Legendrian submanifolds. Now, from contact to symplectic geometry, the road is general and very short. One just needs the notion of Rib vector fields on a contact manifold. A Rib vector field is a vector field on the contact manifold that has the following properties. First of all, the contact form evaluated on the Rib field makes one. So in certain sense, the Rib field is the dual of the contact form. But in order to be really a Rib field, it should be that d alpha, the differential of the contact form evaluated on the Rib field and on any other vector field should make 0. Then, once we have this notion of Rib field, we clearly see that the Rib field is the gradient in the direction of the entropy, is the derivative, the vector field d over d of I. So then comes the following general theorem, that the differential, if we take the differential of the contact form, then this differential of the contact form is a symplectic form, a true symplectic form, on the S2n submanifold of M2n plus 1 that is transverse to the Rib field, namely on those submanifolds of the thermodynamical contact manifold that are isoentropic, namely with fixed entropy. Now, we consider this the projection from M to n plus 1 to the transverse manifold S2n is given by ignoring the value of I, and this projection provides a symplectic manifolds. The question is, what are in this symplectic manifolds, in this projection, the images of the Legendrian submanifolds that are the equilibrium states? They are defined by putting the coordinate xi equal to its calculated value, namely the derivative with respect to lambda I of the so-called stochastic functional, that is, the logarithm of the partition function. So this equations correspond to the embedding in the symplectic manifolds S2n of the images through the projection of the Legendrian submanifold describing equilibrium states. This operation provides the vanishing, obviously, of the two-form, the closed two-form omega, because we make the two derivatives of the stochastic Hamiltonian, and that obviously gives zero. Now, Lagrangian submanifolds of symplectic manifolds are precisely defined as those submanifolds on which the symplectic two-form vanishes. So we come to the final conclusion that equilibrium states are just the Lagrangian submanifolds of the symplectic manifold transverse to the Riemann field. Now we come to the next point, namely Hij, where H is the Hessian, defined here, with d lambda I, d lambda j, is what we can consider as a metric, a canonical metric on the Lagrangian submanifolds, namely the equilibrium states of thermodynamics. Why is it canonical? Because it is the pullback up to a multiplicative constant of the thermodynamical equilibriums on the thermodynamical equilibrium submanifold, Legendrian the full contact space, Lagrangian on the isoentropic leaves, of the canonical metric on the thermodynamical contact manifold, which is the following. So the contact manifold is equipped not only with the contact structure, but also with the Riemannian metric. And the Riemannian metric is precisely this one. Why is it precisely this one? Oh, that is simple. Because if we understand that this is the metric on the contact manifold, if we think what is its projection onto the symplectic transverse space. Symplectic transverse space, this is the metric, obviously, it is an immediate thing. But why is this necessarily the metric on the symplectic thermodynamical manifold? Because this metric is the only one which is generically Kählerian and generically consistent, here T is missing, with the Kähler two-form omega introduced above. Why is it Kählerian? Well, we have just to think about what is the definition of Kähler metric. A Kähler metric is a metric, a Hermitian with respect to a complex structure, and such that the form obtained by making the product of the metric with the contact structure, these two forms should be closed. Now, if we know both the metric and the contact structure, we arrive at the Kähler form. But it can also be opposite. If we know the complex structure and the Kähler form, we can go back to the metric. And this is what we do in this case. We have the Kähler form already defined, and we we look at the only possible um, um, complex structure that can give a metric which is generically consistent with the Hessian. That is what we derive from embedding of thermodynamical states. So we uniquely arrive at this Kähler metric, and then reintroducing entropy to the uniquely defined metric on the contact manifold. Now, at this point, I would like to note something that is extremely relevant. Formally, the Kähler metric on the symplectic RIP transverse thermodynamical space is the same as the Kähler metric for toric Kähler varieties in the so-named MC symplectic formalism, Abreu, Martelli, Sparks, and Yau. It applies to the cases where the Kähler potential depends only from the moduli of the complex coordinates in some complex chart, and that is what makes the variety toric. G is the symplectic real potential, which is the Legendre transform of the Kähler potential, and the phases and thetas are the phases of the complex coordinates. For the interested listener, all that is explained, for instance, in my lecture notes of 2023 at Albert Einstein Institute in Potsdam. What I would like to stress is that in mathematics, when there is a formal identity, that is never without implication and consequences. So this is something to consider carefully, because there is a link between thermodynamic geometry and toric Kähler geometry. Summarizing, probability distribution yields a Gibbs distribution if we consider the approach of James. And that leads to contact geometry that encodes the two thermodynamical principles. Symplectic geometry emerges on isoentropic leaves, and that leads to a Kählerian metric on the leaves. That is precisely the metric of so-called information geometry used in here Laplacian should be Lagrangian. That is precisely the information geometry used in machine learning. This is a completely general scheme. The question is, what are the function SQ on the manifold of events? The answer is simple. In what is of interest in machine learning and mostly in physics is the case where x of q, the functions on the manifold of events, are moment maps of Hamiltonian vector fields. Then this is possible if and only if omega is a symplectic manifold. Namely, the closed-to form exists on the manifold M2N. The closed-to form of maximal rank exists on the closed-to form. And now you can ask yourself why the Sir William Hamilton appears in this picture. The reason is that we will see in a moment, we need Hamiltonian formalism. I will stress at this junction an important observation that coadjoint orbit is the conceptual framework in which Souriau thermodynamics was thought, starting from the well-known Kirillov-Cartan Souriau symplectic 2 form that exists on coadjoint orbits, and if you have a metric, also adjoint orbits of some group acting on its Lie algebra. The orbits are labeled by an element of the Lie algebra, but what I would like to stress is that the orbit, the adjoint or coadjoint orbit of some group Lie algebra element is always diffeomorphic to a coset manifold, namely the group G divided by the mod, the stabilizer of lambda in the group. Now, that means that the stabilizer is never the identity, because at least it contains, its Lie algebra contains the element lambda. And therefore, if we consider all possible coset manifolds, we are also considering all possible coadjoint orbits. So we stick to the point of view of symmetric spaces, which is our choice of special kind of coadjoint orbits, and we say that in this compound, in this province of symmetric spaces, the existence of symplectic form occurs. So we are going to the correct coadjoint orbits. The existence of a symplectic form exists only when the U over H manifold is a Kähler manifold. So now we have a bifurcation. The bifurcation is the following. We have a symplectic manifold, and its Hamiltonian fields and the corresponding moment maps. And there are two ways of interpreting this manifold. Either this is the phase space of the dynamical systems, and the Hamiltonians are truly Hamiltonians. Among them, there is a principal Hamiltonian that is the one that describes time development. And in this case, there is sense in talking about integrability of the dynamical system and Liouville integrability and so on and so forth. Or, on the other hand, we are not interested in any dynamical system interpretation, but we are only interested in the geometry. And therefore, what we look at is the case where the symplectic form is the Kähler-2 form of a Kähler metric, G, on the manifold of events, or in general, the manifold M2N. And this means there is a complex structure associated to the metric, and omega is just the Kähler-2 form. And the moment maps we are interested in are the moment maps of, or Hamiltonians, of Killing vectors. We are not interested in any Hamiltonian vector of that manifold, but only in the vectors that are Killing vectors of the Kähler metric. The interpretation, the use of moment maps in supergravity brane physics is precisely the second one I have just described. And I advocate that this is also the view on the moment maps that is at the origin on one side of Souriau thermodynamics. On the other side, it is also the view of moment maps that occurs in algebraic geometry when one looks at the resolution of quotient singularities via Kähler and hyperkähler quotients, a la Cronheimer. Again, the interested listener can have a recollection of these concepts in my lecture notes of 3 years ago in Potsdam. Then, we are finally coming to Souriau thermodynamics. We have probability distributions defined by the moment maps of Killing vectors of a Kähler symmetric space U over H. The Gibbs probability distribution a la Souriau are defined in the general way, specializing the function P being the moment maps of Killing vectors. Or, as I will advocate, generalization of these moment maps, namely in the ring of polynomials in these moment maps. The partition function is given in this way. This is the integration measure on a Kähler manifold. And the only remaining question, that is the clue of the whole idea of Souriau thermodynamics, is what are the restrictions on the beta vector, which belongs to the Lie algebra of U, in order for the partition function to be to exist, namely this integral to be less than infinity, that is to say, convergent. So what is the space of generalized temperature? Omega t is defined by the condition of convergence of the partition function integral. The answer is that omega t is the adjoint orbit with respect to the full group U of a convex cone in the Cartan subalgebra C of its maximally compact subgroup, or of its abelian extension with polynomials in moment maps of the compact subgroup. Sketch of the proof. This result follows from 4 ingredients. On one side, the use of solvable coordinates, namely the equivalence of the Kählerian U over H with its correspondent solvable groups. B. A general formula derived by Tugent and me 30 years ago for the moment maps in such a situation. C. Cyclic property of the trace. D. The U invariance of the integration measure. The famous formula I mentioned is given here, and I just have to explain the meaning of the symbols. J lambda is a basis of generator of the Lie algebra. Ly is the coset representative in solvable coordinates, so it is at the same time a coset representative and a generic element of the solvable group in matrix representation. And Xc is the generator of the U1 factor in H subgroup U, maximal compact subgroup, that is the algebraic structure corresponding to the Kähler form. Now, the coadjoint with these ingredients, the coadjoint temperature orbits emerge. Why? If I consider any group element of U, I can consider B dot P evaluated not in the point W, but in the point W translated by, acted on by this group element. But because of the structure of the moment maps, the linear formula I gave you, the action of G on W is translated into an adjoint action on the vector of temperatures. So since the measure in the point G of W is equal to the measure, the integration measure in the point mu, that is the property of the integration measure that is invariant against the full group. And by the way, in solvable coordinates, the measure is just the standard Rn measure as a consequence of the diffeomorphism with the Rn. Then the partition function comes out to be, because of that property, invariant against adjoint transformations of the W vector. So the partition function must be constructed only with invariance, Casimirs in the space of beta temperatures. Because of this invariance, we can always bring the beta vector. Obviously, this is true, but assumes that the integral converges. So, assuming that beta is such that it converges, we can bring it to a normal form, beta 0, by using the adjoint transformation that puts it into the Cartan subalgebra of the compact subalgebra. And at this point, one can see that the it is when it is in this normal form that we can see the positivity constraints on the beta 0 temperatures, such that the integral is convergent. Now, the normal form of the Gibbs distribution is therefore the following. We parameterize the Gibbs distribution by the B0 vector that is given by Cartan generators up to a certain dimension of the coset manifolds. And after that, we need some non-polynomial extension thereof to obtain convergence. This is work in progress. This for larger dimension is work in progress, so I will not comment on that. P of I are the moment maps, and obviously G of U is the new solvable parameters of a generic G isometry. So this is the canonical form. In practice, that means that the B0 are the relevant temperature that give the shape of the distribution, of the Gibbs distribution, and instead all the other parameters that have been erased by the G transformation are only those that shift the distribution from a reference point, that is the origin of the solvable Lie group. The identity of the solvable Lie group is the origin of the coset manifold. The distribution can be shifted around and centered around any other point because of the transitive action of the group on the coset manifold. I flash just through the SU11 case, where with these techniques we obtain the explicit form of the partition function, and delta, beta, and zeta are the components of the Lie algebra element, here seen as a vector in Minkowski space because of the local isomorphism SU211 with SO12. So it's J1, J2, and J3, if you like to say like that. The delta, beta, and zeta are the components. And the delta, the partition function, as you see, depends only on the of this object. That is the only invariant in the Casimir of the Lie algebra. Square root of this is the only argument on which the partition function depends. Correspondingly, the Gibbs distribution can be written as follows in terms of the solvable coordinates. To visualize it, we can go from the solvable coordinates to the coordinates, for instance, in the Poincaré disk, and then we can have an explicit view of the Gibbs distributions, and you see that changing the parameters simply means to change the shape and to change the central point of the distribution. So in summary, we have seen that this picture summarized the whole conceptual ingredients. Keller is there all the time, Hamilton is there all the time, and Cartan and Damar are there all the time in order to define what are the layers. We have the two pillars, differential geometry and probability theory, and we have seen how they are intertwined. We can ask ourselves, which are the Kellerian U over H where U is simple? There are two infinite classes, either the Calabi-Vicentini manifolds or the Siegel arrays. The Calabi-Vicentini manifolds are this series of spaces, and the Siegel planes are this series of symmetric spaces. One thing that is important to remark at this point is that there is a canonical embedding of the Calabi-Vicentini into the Siegel plane with larger parameters. And these canonical embeddings are very important, but they correspond to the so-called triangular embedding. I had no time to discuss. It is described in the corpus of papers I mentioned before. Now, another thing I had no time to discuss, and is very much relevant to the compound of application of U over H space to machine learning, is the Tizatake projection, which occurs when the manifold is not maximally split. Now, Siegel manifolds are all maximally split, while Calabi-Vicentini have not maximal non-compact rank, and therefore they admit Tizatake projection, and in fact the whole set of Calabi-Vicentini constitutes a single Tizatake universality class, because they are all they have all the in the whole class they have always the same Tizatake submanifold. That is just, on the other hand, the Siegel plane with the G equal 1, G equal 2. So Calabi-Vicentini have the paint group symmetry, which is again something I had no time to discuss, heritage of supergravity, and of my work in the beginning of the 21st century. And for Calabi-Visentini, we also have the theory of separators in one of described in one of the papers of the corpus I mentioned. The separators are very important differential geometrical ingredients in order to construct the probabilistic differential geometric version of the so-called Infomax distribution, that is a pivot of the categorical perception or classification task in machine learning. So for all this reason, my opinion is that the consideration of Souriau thermodynamics is particularly proficient now at this junction on the Calabi-Visentini manifolds. I thank you for your attention, and I stress that the last observations were put forward as a set of programmatic points for further work by me and my co-authors, but also possibly for collaborations. Thank you once again.